Assalamu alaikum, welcome back. I hope you're enjoying this lecture series so far and the sort of look behind the curtain at how the universe really works as far as we understand and God knows best. Once again, I know that this is probably pretty unusual material if you have not deeply and specifically studied physics, but as I said, I find it very spiritual and I hope you do too. So we had left off talking about symmetry, the underlying symmetry in the universe, and how this is really the key principle around which physics is organized. And we talked about the easy to understand symmetries, more or less, like translation in space, translation in time, rotation in space, and Noether's theorem. And then we said that there is yet a deeper underlying symmetry, a more difficult and more subtle symmetry known as gauge symmetry. And this lecture will be devoted to trying to get just a little bit of a feel for what gauge symmetry means and why it is so significant. It is impossible to do it justice. It is in essence a mathematical symmetry, and without specifically going into the math, we would not be able to get a full understanding, but inshallah we'll be able to get a pretty good feel of this extraordinarily fundamental type of symmetry in the universe. And you may be thinking to yourself, come on, is that really so fundamental? I've never heard of gauge symmetry. Well, again, let me quote to you from the book Symmetry in the Beautiful Universe by Leon Lederman and Christopher Hill. Again, Leon Lederman is a Nobel laureate in physics, and these are quotes from his book, or from their book, I should say. In fact, this has been the dominant theme in all of 20th century physics. All forces, and the italics are his, not mine, all forces are now known to be governed by gauge symmetries, descriptions of which are called gauge theories. And again, from a different page in the book, it became both theoretically and experimentally established that all forces of nature are governed by the overriding symmetry principle, gauge invariance. And in fact, in some sense, the forces are a product of gauge symmetry, and we will talk about that in a bit. But of course, this brings to the forefront or begs the question, okay, what in the world then is gauge symmetry? I can understand mirror image symmetry. I can understand things being symmetric in time, that if I do an experiment today, then do it tomorrow, it should be the same. I can understand translation symmetry. If I do an experiment and establish a law of physics and then move 10 feet over, that same law of physics should apply and so forth. But what is gauge symmetry? Okay, to start trying to answer that question, let us look at this map of the world, and I'm going to use an analogy that I owe to the mathematician Timothy Nguyen, a beautiful lecture on YouTube introducing gauge symmetry to non-experts if you want to look it up. But you look at all of the different countries, they are, different colors. And we know that each country has its own currency. So in the US, I use dollars. If I go to Mexico, I'll use the peso. If I travel across to Japan, I would use the Japanese yen, and so forth. And so each country has its own currency. And we can see that on sort of a world currency map, if you will. And this is a little bit difficult. American dollars, Canadian dollars, British pounds, Russian rubles, and these currencies may change. So if I go from the US to Mexico, the peso is about 20 pesos to the American dollar. So if I have 10 American dollars, I would have 200 Mexican pesos. Now, you and I realize that I haven't made money when I go from the US to Mexico, and now I have 200 units of Mexican money, but before I only had 10 units of American money. right? It's just the exchange rate that keeps the underlying wealth equivalent. Or if I go from the US to Japan, well, the exchange rate there is about 126 yen per dollar. So if I have 10,000 American dollars, I can't go to Japan and say, oh, wow, now I am a millionaire because I have a million point 26 Japanese yen. My wealth is still $10,000 equivalent buying power. And these currencies, of course, are arbitrary. They are not any sort of physical law. They are just arbitrary units that could be changed. So, for example, we could in the US take all of the George Washington $1 bills and destroy them and say we're only going to use the Benjamin Franklin dollars, which are, of course, the $100 bills. So all of a sudden, the US currency would be reset to 100 times its value, and each dollar would be worth 1% of the new currency, right? If I have one American dollar with a George Washington dollar, then I have only 0.01 Benjamin Franklin dollars, which is the $100 bill. So not only are the currencies different, but they are arbitrary, and each country can decide to reset its currency. And so the fact that these currencies can change, but I know that wealth should stay constant, the buying power stays constant, that in and of itself requires a so-called connection field between the different countries vis-a-vis currency. And that connection field is what we know as the currency exchange rate field, if you will, that if the US adjusts its dollar, then all of the exchange rates would adjust to reflect the new value of the dollar, and so on for any country. And that can happen locally. Any country can adjust, or all countries can adjust, and the currency exchange rate field will adjust, and it is required to keep wealth constant. So even though the number of dollar units I have, 10 American dollar units versus 200 Mexican peso units and so on, those numbers change, but the wealth stays constant because of the presence of this connection field that makes sure that the wealth stays constant, that there is an equivalency. That is the best example I have ever heard of what a gauge field is. This gauge field, or this connection field, maintains the gauge symmetry or the invariance. Remember, what a symmetry means in physics is an invariance, that under some sort of transformation, like a transformation from dollars to pesos, the underlying important thing, which is my wealth or buying power, does not change. It remains invariant. And so this is, in some sense, what a gauge invariance or a gauge symmetry is. Here we've been talking about currencies, and you may be wondering, well, in the physical world, in the world of quantum mechanics or particle physics, what are we talking about that stays invariant? Okay, so here is where I'm going to now lapse into a little bit of jargon, and I do this just so that if there are viewers who have studied physics in some depth, I am also addressing things to them. If this doesn't make any sense, and it should not make any sense to the vast, vast majority of listeners, please don't worry about it. I think we've already covered the substantive material. But we talked about how the standard model, the particles of the standard model are really an expression of underlying fields. Electron field, the field for the gluons, the field for the quarks, and so on. And fields are expressed mathematically in the language of waves, and they use complex mathematics. And I don't mean complex as in complicated or difficult. I mean real numbers versus complex numbers, things in the complex plane or complex domain, which have real parts and imaginary parts, if you remember complex numbers from high school or college math. And waves have amplitude, frequency, and a phase, and the complex or imaginary part interacts with the phase of a wave. And the phase of a wave, a sine wave is a sine wave is a sine wave, and its phase doesn't change its identity. And so we can take any field and multiply it by a phase term and locally vary the phase or impose a so-called rotation in the complex plane. And that would be the equivalent of different currencies in different parts of space. And so the presence of this notion of being able to impose a different rotation in the complex plane on any one of these fields requires that we then have a connection field so that the important things stay invariant. And that is what the gauge field is in particle physics. And so from this website here, physics is preserved under a local gauge transformation only if there exists a vector gauge field that couples to the system. And that gauge invariance of the field can be exploited to cancel the bad terms the local transformation generates and restore physics. So for example, if I take an electron field and change the phase, it would seem that I have altered visible properties of the electron, like, for example, the energy or the momentum. But the energy and the momentum should stay constant. And so the gauge field that gets produced interacts with the electron field to restore the true momentum or energy of the electron, for example. So I know that if you haven't studied this, it makes zero sense, but it is just like needing a currency connection field if each country can arbitrarily change its currency so that my wealth stays constant. And let me say here that there's not just one gauge symmetry. There are different types of rotation in the complex plane. So on the two-dimensional plane where I'm just spinning around in a circle, that's one type of transformation. If I have a three-dimensional space, I can rotate in that space as well and so forth. Okay, I don't really want to say any more about that, but how are all of these fields and symmetries and so on expressed? They are expressed in this mathematical beast known as a Lagrangian that I touched on earlier. And this is the Lagrangian of the standard model of particle physics. It has these different terms. These are the gauge symmetry terms. And there's a U1 symmetry that it has to do with the electromagnetic force. There's an SU2 symmetry, standard unitary symmetry group, that has to do with the weak nuclear force, and an SU3 gauge symmetry that expresses the strong nuclear force. And then a whole lot of other terms with different bits and pieces, different fields interacting with each other. So the only way to really express this, or I shouldn't say the only way, but the way it is expressed is in terms of this Lagrangian. And this thing that can be put on a t-shirt is the most predictive thing that modern science has ever produced. There is essentially no experiment which is not accounted for by this Lagrangian. What you saw before was sort of a compactified Lagrangian with matrix indices kind of buried into compact notation. This is the unfolded L here, SM, the Lagrangian of the standard model. This is it in its full glory with all of the gauge symmetries built in. And now you may say, why in the world would we complexify all this? Well, because all of the forces are really expressed in terms of gauge symmetry. And I want to say two takeaway messages. Takeaway message number one, gauge symmetry significantly restricts the terms allowed in the Lagrangian. If you say that I am going to assume or force the physical laws to obey gauge symmetry, then only certain types of forces come out. That is related to fundamental point number 2, is that the presence of a gauge field, the presence of a connection field, in and of itself has physical consequences. We said there's an electron field, it produces electrons. There is a quark field, it produces quarks. Well, if we impose gauge symmetry, then we see there has to be a connection field or a gauge field, and it turns out that these gauge fields themselves produce things and have very significant consequences. And we're going to look at that in a second, but let me just, when I say that the gauge symmetry restricts the form of physical laws or the terms allowed in the Lagrangian, let me give you a very simple analogy back to our currency connection field. That currency connection field forces the transformation of currency to be linear. What do I mean by that? I mean, if I have 10 American dollars, they are worth 20 Mexican pesos. Now I double that. If I have 20 American dollars, they are now worth 400 Mexican pesos. 10 goes to 200 because the exchange rate is 20 to 1. Then $20 would then go to 400 because the exchange rate is again 20 to 1. It is a linear transformation. I just multiply by that constant conversion factor among currencies. A power law is not allowed. I can't say that it is going to be the American currency squared, so that if I have $10, it would go to 200 Mexican pesos, but if I have $20, well, I'm going to square it, and now I will have a square law. No, it has to be a linear transformation. If I double the American money, I double the Mexican pesos money. So that would be how a gauge symmetry would restrict the form of a physical law. And so gauge symmetry ends up being very, very important. And finally, now coming to the end of this lecture, and I know many of you are probably saying, thank God, what are the results of this gauge field or these different gauge fields that we really have talked about? Well, just like electron fields result in electrons, the gauge fields result in gauge bosons. And so the U1 gauge symmetry results in the photon, and that is the force carrier for electromagnetism. The SU2 group results in the W and Z bosons, and that they are the force carriers for the weak nuclear force. The SU3 symmetry group is tied into the gluons, and that is the force carrier for the strong nuclear force. So in a very significant sense, the forces of nature are a result of the gauge symmetries. They are the palpable product of the presence of gauge fields. And so you may ask, well, why should the universe have an electromagnetic force? Because it obeys a U1 symmetry. Why is there a strong force, and so on and so forth? So forces are, in some sense, the result of gauge symmetry, of the underlying gauge symmetry of the universe, and that is why it is so fundamental and so critical. Finally, again, this Higgs boson sitting here in the corner, and once again you may think that we have just drifted way off. What in the world does this have to do with the Higgs boson? Well, inshallah, in the next lecture, we will finally start to bring it back home and talk about what all of this stuff has to do with the Higgs boson.